Atomic absorption spectroscopy. Introduction. The first observation of atomic absorption spectra was made by Fraunhofer while studying dark lines in the solar spectrum. The potential use of atomic absorption spectroscopy for the analysis of metallic elements was first pointed out by Walsh and by Alkmaid and Miltaz in 1955. The technique is particularly useful in the determination of trace metals in liquids. The versatility of atomic absorption spectroscopy can be gauged from the fact that 60 to 70 elements can be determined by this method in concentration as low as 1 ppm. The greatest advantage of atomic absorption spectroscopy is that the analysis of one metal in the presence of another metal can be carried out, saving time and eliminating error. The principle of atomic absorption spectroscopy involves the study of absorption of radiant energy, usually ultraviolet and visible, by neutral atoms in the gaseous states. If light of the resonance length is passed through a flame containing the atoms in question, then part of the light will be absorbed, and the extent of absorption will be proportional to the number of ground state atoms present in the flames. This is the basic principle of atomic absorption spectroscopy. If the technique involves spraying a solution of the sample into the flame, it is referred to as absorption flame photometry. And if it is based on the re-emission of absorbed energy via free atoms, it is referred to as atomic fluorescence spectroscopy. Atoms absorb light at a definite wavelength depending upon the nature of the element. For example, sodium absorbs at 589 nanometer, potassium absorbs at 766.5 nanometer, and uranium absorbs at 358.5 nanometer. Light at these wavelengths have adequate energy to excite atoms to another electronic state. From the ground state, an atom is excited to a higher energy state by absorption of energy. Now, there can be several excited states with definite energies. Atoms do not vibrate, and also there is virtually no rotational energy associated with them. Hence, only electronic transitions of the outermost electrons give rise to a series of well-defined narrow lines forming atomic absorption spectra. Atomic spectra are identified by the sharp line of maximum intensity, and it can be distinguished from broadband spectra associated with molecules. Atomic spectrum is peculiar to each element and consists of discrete lines including resonance lines, that is, lines which arise due to transition from ground state to excited states. The total amount of light absorbed by atoms can be given by the expression nu is equal to pi e square upon mc into nf, where E represents the electronic charge, m is the mass of electrons, c is velocity of light, n is the total number of atoms that can absorb at frequency nu in the light path, f is the oscillator strength or the ability of each element to absorb at frequency nu. The total amount of radiation absorbed can then be given by the expression constant into n into f. This expression does not involve wavelength, therefore frequency and temperature. Atomic absorption is thus independent of wavelength and temperature and is advantageous over other atomic spectral methods such as emission and flame spectroscopy. Atomic absorption peaks are much narrower, that is, they are of the range of 10 to the power minus 4 angstroms, than those observed for ions or molecules in solution. These lines may be broadened to an observable dimension ranging between 0.02 to 0.05 angstrom by two effects. The first effect is the Doppler broadening effect. Doppler broadening arises due to rapid motion of the absorbing particles. The Doppler effect causes the radiation to effectively decrease in wavelength for those atoms which travel towards the source, and somewhat longer wavelengths are observed for atoms moving away from the source. The second effect which can be used for broadening the lines is the pressure broadening. The collisions among atoms produce small changes in the ground state energy levels, and consequently broadening of peaks occurs. This is called pressure broadening.